Hi everyone, this is Gaurav and today we'll be studying a topic from control system, and today's topic of discussion is basically we will be getting to know what actually the transfer function is, what actually the linear time invariant systems are, and how block diagrams can be analyzed. We will be taking an example of block diagram and further a small methodology and element structured concept which is basically used in block diagram. We will be taking care of all those aspects of block diagram. So in this presentation, following three topics we will be covering, and in the next topic, next control system lecture, we will be studying the block diagram reduction methods. Okay, so let's start. So what actually the transfer function? Okay, so our next slide is basically about the transfer function. So if I ask someone that what actually the transfer function, so transfer function is basically the Laplace transform of output with respect to Laplace transform of input. And key point is this, that we have to keep initial conditions which should be 0. So it is the Laplace transform of output with respect to Laplace transform of input, keeping all initial conditions 0. Mathematically it is represented as TS, which is the ratio of output response with respect to input. Where CS is the Laplace transform of output and RS is the Laplace transform of input, keeping all initial conditions 0. And one key take from this particular slide is this, that for non-LTI system, transfer function cannot be defined. For non-LTI system, transfer function cannot be defined. Now let us understand this transfer function methodology with the help of a numerical. So hereby in this numerical, you have to determine a transfer function. Okay, you have to determine a transfer function of the circuit. So here is the circuit. Here is a circuit which is in time domain. You can easily see that the circuit is in time domain. V1t is in time domain. V2t is in time domain, and we have to obtain the transfer function. So we have to convert it into S domain, that is Laplace domain. Hereby you can easily see that V1t, which is in small letter, when it is converted into Laplace domain, V1t has become V1s and it is in capital letters. Likewise V2t has become V2s. Likewise 2 Henry inductance is represented by SL. Okay, so here I have written SL, which is S multiplied by L, and the value of L is 2 Henry, so it comes 2S, and it is resistance 20 ohm, and the same thing it will come at the Laplace domain, that is 20 ohms. Now here this particular system is subjected to two types of input. If the input is suppose V1t, that is 20 for t greater than 0. So here V1t is basically 20 for t greater than 0. It means V1t would be 20 volt DC supply, okay, and for t greater than 0, it is providing a concept that this particular signal is a step signal having an amplitude of 20 volts. Okay, so I told you that all the time domain variables we have to convert it into Laplace domain. So what we did, we just calculated V1 as that would be 20 by S. Okay, and further we put this value into consideration, whereby a transfer function is defined as output by input, whereby we can keep the value of V1s, that is the input, and V2s can be easily obtained by by just implementing or uh, taking input loop and output loop KVL loop equations. Okay, so you can just analyze, and in the second case we have taken a sinusoidal input and it is a AC input, and we can say that it is single phase supply and it is having an amplitude of 20 and frequency, angular frequency, that is 10. Okay, so hereby again we will just take a Laplace transform of input, and you can easily see that we have converted V1t into V1s. Okay, and hereby V1s is basically is like this. So thereby a transfer function we can easily analyze, and we can do the mathematical analysis, and we can easily obtain the transfer function, which is basically the output by input Okay, so moving ahead and taking the another slide whereby we can understand what actually the linear time invariant system is. So as we split this particular terminology, firstly a term comes linear. Okay, how we can analyze a system linear or not? So here is the definition of linear system whereby it is said that it should follow the principle of superposition. Okay, it should follow the law of additive and homogeneity. And third very important point, that is it is independent of time scaling. Okay, it is independent of time scaling. Okay, and there are few example: x of t, x of 2t, x of t sine omega t. When we say that it follows the principle of superposition, it means superposition means that in a suppose multiple input multiple output system. Okay, and superposition says that we have to consider a single input and we have to keep the other inputs, or we have to keep the other input deactivated. Okay, so we have to keep the one input and other inputs deactivated, and from that input which is active we have to calculate the output. Okay, as the system is a linear system, so law of additive is followed. Likewise, in the second case, we have to take another input and keeping other inputs deactivate and calculate the output with respect to that input, and further just addition of all the outputs. So linear system follows the law of superposition and law of additiveness. So this is the linear system concept. Likewise, in time invariant system, a very important thing is this: if you are providing a delay at the input, suppose you are providing a delay at the input, x of t is there, okay, and you are providing a delay. So delay means that it would be x t plus 5. So that t plus 5 should also reflect at the output y t plus 5. Okay, likewise, hereby in example you see, just we are not providing any delay at the input, so we are not getting any delay at the output. Okay, so that and if we apply a delay, that is t minus 5, sorry, t plus 5, like then that particular delay will certainly addressed or reflected at the output yt plus 5. Okay, if it becomes xt minus 5, then output will certainly become what actually the output? Yes, then output will certainly become yt minus 5. And in the second case, you just see, we are having a time, okay, and that is getting multiplied by 2, but that 2t is not reflected out the output. Okay, it means the system is time variable. Hereby in input, you can see that time is multiplied by 2, but this particular terminology is not reflected at the output. So this is the example of time variable system. Now, what actually the response or a behavior of the process or plant? Actually, what we have seen when we just providing a input to a plant or a process, what actually happens that in a practical case, the output of the system will not instantly follow the input. Okay, why so? Because in our process, in our behavior, we are having different types of components, and some components are energy dissipating and some components are basically storing elements. So there would be transition of state just because of storing nature of those elements. So the output will certainly not, or you can say the output will not instantaneously change with respect to input. Okay, so response or a behavior of the process or plant is basically depends upon the ZIR plus ZSR. ZIR is basically the zero input response, and ZSR is basically the zero state response. Okay, what actually is a ZIR? Zero input response. It means in zero input response, if you just see the output obtained when input is zero due to initial condition. Okay, the output obtained when input is zero due to initial condition. It means that you are not providing any input, and even though you are getting an output. Okay, so what could be the practical scenario? Yeah, scenario would be, suppose if you are having a charged capacitor in a circuit and you are not providing an input, even though just because of the charged capacitor you are getting an output along a particular element. Okay, so that is ZIR. Likewise, ZSR would be basically the output obtained only when the input is applied. Okay, but we have to deal with a transfer function. So we in the definition of transfer function says that we have to keep the initial condition zero. It means while designing, while or defining a transfer function, we cannot use this ZIR. Okay, or this ZIR should also become zero. Okay, hereby in these three lines we have written this thing to uh, that if you have to obtain the transfer function, the ZIR should also be zero, and it is only possible when initial conditions are not considered. So it means there are various uh, advantages and disadvantages of transfer function methodology. So before moving ahead towards the advantages and disadvantages of transfer function, we should take an example that how a transfer function can be defined and what actually the poles are, what actually the zeros are, and what would be the order, what would be the type of the system. Now, in front of your screen, you will be seeing a transfer function, okay? And this transfer function is the ratio of Laplace transform of output with respect to Laplace transform of input. Okay, so this transfer function consists of some zeros and some poles, and zeros basically denotes the numerator of this transfer function, and poles basically denoted by the denominator uh, polynomial equation. Okay, so you can easily find this thing that there are four poles. Two poles are at origin. Okay, two poles are at origin, and there is a s equals to minus 2, that poles comes on the left side of the s plane. Likewise, there is another pole s equals to minus 3, that too comes on the left side of the s plane. And here are two zeros are there, s plus 5 and s plus 7, that is s equals to minus 5 and s equals to minus 7, and these two zeros also comes the left side of the s plane. Okay, so no, few question can arise over here by seeing the transfer function. Someone can ask you that how many storing elements your system consists of. First question. Second question could be what is the type of the transfer function. Third question would be what would be the order of the transfer function. Okay, and fourth question could be that identify poles and zeros. So hereby I just told you that poles are basically, hereby poles are, four poles are there and two poles are at origin. Okay, now so poles and zeros we get to know, minus 2, minus 3, and two poles are at origin. Zeros, roots of the numerator of the equation, s equals to minus 5, s equals to minus 6, minus 7. Okay, s equals to minus 5, s equals to minus 7. Likewise, what actually the order? Order is basically the maximum order of the polynomial equation in the denominator. So in this particular expression, the order is 4. Okay, and whatever the order would be, the number of storing elements are same. So here by order is 4, so number of storing elements would be 4, number of state variables would be 4. Likewise, what is the type of the system? Often it is asked, so you must remember the number of poles at the origin, number of poles at the origin, number of poles at the origin. So in this case, number of poles at the origin are basically 2. So the order of the system would be 2. Suppose if this s square term is not coming, then in that case the type would be 0 and there would be no pole at the origin. But in this particular numerical we are having s square, so number of poles are 2 at the origin, and it defines the type of the system. Moving ahead, what actually the advantages and disadvantages of transfer function. So as you are very much aware that from the help of transfer function we can analyze number of poles, number of zeros, type of the system, order of the system, how many storing elements are there, what would be the order of differential equation is, and what actually the disadvantage, if you'll see that it is only applicable for linear time invariant system and internal states cannot be determined, and it is applicable for single input single output. If we are having multiple input multiple output systems, then we have to decouple it into single input single output system. Controllability, observability cannot be determined. So this is also a case with this transfer function methodology. Okay, now moving ahead to the important slide, that is block diagram method. We'll be briefing you what actually the block diagram could be with an example, and we'll be analyzing that how that multiple input multiple output block diagram can be decoupled into single input single output block diagram, and for analysis purpose Then further in this, we will be taking care of basic elements of block diagrams and how blocks are connected into series and how their gains are multiplied. So in this particular segment, we will be taking care of all these aspects. So let's start. So here is the example in which automobile driving control system is studied. You can easily find in this particular block diagram. First, whenever you just see the block diagram, try to analyze where is the plant, where is the process. So in this, the plant and process is vehicle, okay, and this vehicle is basically a four-wheeler, or you can say. Now, this vehicle consists of steerings, okay, steering, wheel positions, and the brake and accelerations. So, which basically take care of your accelerator. Now, this vehicle do have two state variables, okay. First state variable in which direction it is heading, okay, and in the second variable the speed, okay, because speed depends upon various factors like where you are going, is it a crowded area or not, okay, or it is a smooth road, and suppose there would be some speed breaker, then you have to reduce the speed. So speed is also variable. So there are two state variables, heading the vehicle heading towards which direction and the speed of the vehicle. Likewise, there would be two reference input in the same pattern. There would be a direction of highway. At least you must know that in which direction you should go. Okay, you know the destination. So direction of highway is the state, direction of the uh, highway is the reference input, and likewise the speed limits are also the reference input. Now, the heading of direction and speed is governed with the help of some sort of controller. Okay, and here you can see there is a control logic. Automatically, your brain is trained and practiced. So, brain and is easy way which we or which the person who is driving can take care of and analyze the differences between the inputs and the outputs. How he will analyze the inputs? That brain will provide a signal or a control action to your hands, okay, so that your hands will take care of the steering of the four wheeler. Likewise, your foot will take care of the brake position or the accelerator. Okay, there are two by foot we can just accelerate, and also we can use the brake positions. So this is the block diagram, and this block diagram is taken from the reference book, that is Principle of Design Control System, M Gopal. Okay, and M Gopal, Professor M Gopal is a prestigious professor in teaching in IIT Delhi, and lot of impetus and very nice book it is. Okay, now I told you that we have to analyze the system, and we have to just decouple this system into a single input single output system to analyze for the transfer function. So here are the key points from this block diagram. First block diagram key point is that system to be controlled has two inputs, is steering and acceleration braking, and two control output, that is in which direction it is heading and what actually the speed. And the two command inputs are in the direction of the highway and the speed limits with traffic signals. And this block diagram is multiple input, multiple output. And to analyze the transfer function, we have to decouple this block diagram into single input, single output. Okay, so here is the functional structured block diagram in front of your screen. Hereby you can see that each block, what we have studied in a previous slide, each block or any type of control system can be modeled into some sort of gain. Okay, so here you can see this is the gain element A, this is the gain element D, this would be gain element or amplifier gain, and this would be the plant transfer function or a plant gain, and here could be some sort of disturbance in the input, and here some sensor gain is there. So likewise, block diagram is structured in this pattern. Okay, and when the block diagram is structured in this pattern, we can easily deduce reduced form of block diagram. Okay, so this is this particular section defines the controller, this particular section will define the plant, and here are the key takes which you can easily read it out and what I get to take. So this is basically M, what actually the manipulated signal or a control action which is providing to the plant. Okay, so this particular B point defines the signal which is coming from the feedback. Okay, that would be Y multiplied by H. and what actually E would be what? R minus B. Okay, what would be U? The value of U would be E multiplied by D. Okay, so this could be analyzed. Now let's take another slide and try to understand how to reduce the block diagram. So can you tell me, is this the example of open loop control system or a closed loop system? So you can easily see that there would be no feedback. So it means it is the block diagram of open loop control system. Now, in a very smooth way, I can tell you one thing that when we are going to calculate the transfer function, or when we are going to calculate the gains of a function. So suppose if I ask you that what would be the value of CS? Okay, so you can see the if someone asks you the value of CS, it means that we have to see the gains coming prior to that CS block. Okay, we have to see the gains coming prior to the CS block. So the gains which are coming at the prior is basically, suppose there is a stimulus, that is RS. Okay, so RS would getting multiplied by GS. Okay, as it is in the direction of CS, so RS is getting multiplied by GS. The value of CS would be what? RS multiplied by GS. Okay, so the value of CS would be RS multiplied by GS. Suppose at this point, okay, suppose at this point, if we are measuring this particular value of CS, it means there would be some sensor at this point. When there would be some sensor at this point, it means some sort of HS would be there, sensor gain. Then what would be the value of CS? Then value would be RS multiplied by GS multiplied by HS. Okay. Now what we have to do, we have to obtain the transfer function. So as I told you, you got the value of CS, that is RS multiplied by GS. So just rearranging CS by RS would be GS. So this is the transfer function. Key take is basically, in case output is measured by sensor, I told you HS would also come. So the transfer function will get multiplied by HS. Okay, so HS is basically sensor gain. Now here is some sort of mechanism where you can see there are three subsystems, and these three subsystems are in cascade manner. And the subsystem one is basically subjected by input R of t in a time domain, you can say, and we have to calculate the value of output or a transfer function. Now, what actually you will see that this particular figure number one, this figure is getting converted into Laplace domain, and you can see that subsystems are represented by their gain. Subsystem is one is represented by the gain G1s, subsystem 2 gain is represented by G2s, subsystem 3 gain is represented by G3s. And I told you, if suppose if someone asks you what would be the value of ys, so it means the gains prior coming to the ys would represent the value of ys. The gains which are coming to the prior are basically G1 multiplied by G2 multiplied by G3 multiplied by RS. Okay, so this is the basically the value. Now, what actually Y1s, Y2s represent? Y1s is basically the output of subsystem one. Okay, the output of subsystem 1. Likewise, the Y2s is the output of subsystem 2, and YS is the output of subsystem 3. So Y1, which is the output of subsystem 1, will act as an input for subsystem 2. Likewise, Y2s, which is the output of subsystem 2, will act as an input for subsystem 3. Okay, so here by a reduced block diagram, all gains are multiplied when they are arranged in a pattern of a cascading in a direction of flow. So uh, here is the transfer function ys by rs can be defined as g3 multiplied by g2 multiplied by g1s. Now here is the concept of key elements which should take care of when we talk about block diagram method. So this is the A1 A the figure number A, which is very basic figure, and this figure is we have studied in open loop system. This is the figure number B. This is the case of cascading block diagram where gains are multiplied. Here summation of gains, okay, over plus plus, and here there would be some sort of negation, plus minus, and this particular point is a takeoff point. Okay, when we were studying this structure block diagram, you can easily find this takeoff point y. Okay, so any signal which is fetched at this particular point and it is coming to some sensor or some sort of element, so this would be the takeoff point. Okay, so that is represented, and that is also a key element, takeoff point. In block diagram methodology deduction method, this is very essential, and there is a concept of this takeoff point. Now, let us consider a block diagram of a closed loop control system. When we talk about the block diagram of closed loop control system, we have to find the transfer function. So the transfer function would be the ratio of CS by RS. Okay, the transfer function is the ratio of CS by RS. How we can obtain this CS by RS? We will consider some equations, and those equations are rearranged, and we can easily obtain the transfer function. Okay, so this particular GS will certainly represent controller gain or controller gain multiplied by plant gain, and GS would also be set as a open loop gain, and HS would be the sensor gain. Now, when we have to calculate the value of CS by RS, we will take three equations. So in equation number one, you can see the value of CS is ES multiplied by GS. So I told you that if you have to calculate the value of CS, we have to take care of the gains which are coming before the CS, so in the direction of flow. So if the value of CS, if we have to calculate the value of CS, the gains prior coming to our ES multiplied by GS. So see the value of CS, I wrote ES multiplied by GS. Likewise, if someone asks you what would be the value of BS, so what would be the value of BS? Over here we are having CS, over here we are having CS. So CS getting multiplied by HS. So the value of BS would be CS multiplied by HS. Okay. And what would be the value of ES? ES would be what? RS minus BS. So I wrote ES equals to RS minus BS. Now, if we put the value of ES and BS from equation 1 and 2 in equation 3, and we will arrange these equations, and we can easily find the transfer function that is between the CS by RS. Okay, and the closed loop transfer function, here it is here it is a negative feedback. Once you arrange these equations, you will get a transfer function for a negative feedback, that is CS by RS, that is equals to GS by 1 plus GSHS. Okay, GS by 1 plus GSHS. Okay, fine. And when we consider a positive feedback, when we consider a positive feedback, the expression would come like this: GS 1 minus GS HS. GS 1 minus GS HS. Okay, in positive feedback, you are very much aware what we will do. We will just provide a feedback over here, positive. Okay. So this is the case of negative feedback, positive feedback expressions. You must remember that for negative feedback, it is coming the polynomial denominator equation, whereby you can see that this expression is coming 1 plus GSHS, and in the positive feedback, the expression is coming like this. Okay, 1 minus GSHS. Now, what would be the difference in these two equations? Okay, the difference is very common and very easy. You can find that for negative feedback, you will 1 plus GS HS it is for negative feedback 1 plus GSHS. Hereby gain is reduced. Overall gain is reduced because the denominator term is basically higher. And in the for positive feedback, you can see that overall gain will be high. Overall gain will be high as compared to negative feedback, because here in the denominator it is used 1 minus GSHS. Okay, so the denominator term is less, so overall gain would be high. So this is the case of negative feedback and positive feedback. So these are the slides. You can once again go through these slides and analyze everything. Try to practice some questions. Try to take some examples, whereby in those examples you can learn how to find out the transfer function and how things can be analyzed. So I hope these slides are very much uh, easily accessible to you, and you can easily analyze these slides. Okay, so this is all about this presentation. And if you have any doubt, please do comment, and you can just mail me. My mail ID is classgoeducation@gmail.com.